Good afternoon and welcome to another Reliability Web workshop. If you're looking for the workshop on an animated introduction to vibration analysis presented by Mr. Jason Tranter, then you are in the right place. My name is Bill Partitillo and I'm going to be your moderator for today. Here at Reliability Web and Uptime Magazine, we base everything on the Uptime Elements framework located on the chart on your screen. Today's presentation will focus on the asset condition management domain, which is located in green. Today's presentations will focus on the following three items. How does vibration analysis provide a key insight into the health of rotating machinery? Where does the spectrum come from and what does those peaks mean? What does the time wave format and phase reading tell you that you cannot learn from the spectrum alone? Please don't forget to subscribe to Uptime Magazine, the magazine for maintenance reliability professionals. There is absolutely no cost to subscribe. If you are interested, go to www.uptimemagazine.com. Please mark your calendars for the Solutions 2.0 conference in Houston, Texas, August 3rd through the 7th, 2015. Solutions 2.0 will feature presentations on asset condition management, reliability, risk management, asset information, and asset decisions. If you would like to attend Solutions 2.0 in Houston, Texas, please visit www.solutionsconference.info, which is located on your screen. All right, it's time to introduce Mr. Jason Tranter. Jason, are you there, sir?
Yes, I am.
Welcome. I'm going to pass this over to you, Jason, right now, and you should start to see it on your screen.
There we go. Are you seeing me?
Jason, we see you. Everything looks fantastic. Welcome, Mr. Jason Tranter. We look forward to your presentation.
Thank you very much, and I do apologize for the late start, but hopefully we'll make up for that delay. Okay, as Bill mentioned, this presentation, an animated introduction to vibration analysis, is going to attempt to introduce each of the main vibration analysis technologies to you in the next little while. The aim, of course, is to find out what's going on with our machine and I guess to some extent the supporting structure so that we can plan some maintenance and ideally so that we can also identify those root causes that might cause the machine to fail, like unbalance and misalignment and other conditions that will lead to bearing faults. So let's get started. Now I hope this connection is going to work. We're going to show a lot of animations and hopefully they'll come through the GoToMeeting process smoothly. But obviously what we want to avoid is any equipment failure and all the downtime and safety issues that can occur because of the failure. We certainly don't want that to happen to our machines. So what we'd really like to be able to do is get inside the machine and see what's happening as the gears mesh together and the bearings roll around and all that sort of stuff. We want to be able to do that, and that's what vibration analysis does for us. Because if we can understand what's happening, for example, inside the bearing, and we can tell whether the balls are just rolling along smoothly without any damage to the raceways or any damage to the rolling elements, then that gives us a clue. If we can tell that there's a lubrication problem that might lead to a further problem or a misalignment or an installation problem, that's important. And it's the same with gears, whether they're from a gearbox or timing gear or anything else. We want to make sure that that mesh is occurring properly, that there's proper lubrication and all those things. And that goes for every component within the machine. So in this instance, we've potentially, well, we are interested in the rolling elements themselves, the health of the rotor itself and the windings in the stator and the rotor. We're interested in the coupling and the vanes in the pump, make sure we don't have cavitation, and certainly the bearings on either side. And you may not be able to hear this very well, but we want to individually listen, if we could, to what's happening to each of those individual components and find out, is it healthy? Is it sounding okay? Now with ultrasound, we might literally listen to it. But rather than that, we're going to use vibration analysis and use various techniques to really drive home and find out what's going on. Now, if you're brand new to vibration analysis, the basic idea is we're going to put a sensor on the machine, and basically all the vibration, is making the machine vibrate as a whole. As part of that, it's going to move up and down. So a sensor up on top of that bearing is not only going to pick up the vibration from that bearing, but from the other components. All the vibration sort of travels along the shaft through the bearing, the housing, and so on, up to the sensor. But the sensor there is sensitive to the vertical motion. And with some faults, we can see a lot of motion in the horizontal direction as well. It might rock or sway from side to side. If there was a looseness problem or a problem with the foundations, we're interested in that. We are also interested in the end-to-end or the axial motion as well. But we need to test each of the bearings because the vibration, particularly high frequency vibration, which I'll mention in just a moment, doesn't necessarily travel from those bearings along the shaft to those bearings. So that's basically what we need to do. We should measure the vibration in multiple axes, if at all possible, which includes axial as well. And we need to monitor as many bearings as we can to really make sure we are detecting all the problems that are going on. Now, if we go to the real basics, and we'll start from a position that I guess everyone should be familiar with, that if we had a shaft moving in this circular motion, now, we would never physically see the shaft do this. I'm exaggerating the motion, but if, for example, there was some unbalance, the shaft wants to move in that circular motion. Now, if we could hook up a dial indicator as shown, the needle would swing back and forward and we would get that pattern if we looked at it over time. And this is the fundamental of everything we deal with. It's called the sine wave. It represents one frequency of one amplitude, because in this little simulation here we are only looking at the motion of that shaft. Now, of course, we're not going to use a dial indicator. We could use a displacement probe, which is sensitive to the actual movement of that shaft versus the bearing itself, or wherever the probe is mounted. Now, we use those on turbines, and we can use those on machines with journal bearings or sleeve bearings. We used to use velocity probes, but we'll focus on accelerometers, and the only difference being we take that accelerometer, mount it on the bearing housing, and because the shaft is trying to move in this circular motion, and because there might be damage to the bearings themselves or all those other things we just mentioned, that vibration all sums together and makes the bearing housing want to move. But ultimately, if there was just one source of vibration, we would have just one simple signal like we see here. Now, if the machine moved faster, as in rotated more quickly, it'll move back and forward more quickly, the sensor picks that up, and you see the change here. This is now a higher frequency. On the other hand, if we had more movement, the unbalance is now worse, we see more movement and the sensor picks that up and we see higher amplitude. Now again, this is just one source of vibration, and if we had a fan on it, I mean, this looks a bit odd I suppose, but we now are just picking up the motion that you might see if there was a problem with the fan blades themselves. It is a higher frequency because in this case we have 6 blades, and that's a sort of a simplification, I guess, of how it would move if, as each blade went by, there was 6 times per revolution, we end up with a higher frequency. And if we had movement of the shaft and the fan blades, we get a combination. There's a combination of both motions. The sensor picks that up, and therefore we see a combination of both signals. The higher frequency, because we've got 6 blades, and you can see that there's a lower frequency in there because of the once per revolution motion, which may be due to unbalance. So that's the basics of the raw signal. Now, that's all great, but looking at that sort of a signal makes it a bit complicated to look at it and recognize what's going on. So that's where the spectrum comes into it. Now, there's our machine, a bit more of a real-world situation here. If you look really closely, you might see that the shaft as it's turning is wobbling a bit. So now, what I'm going to do with these buttons, I can turn on the vibration from each source. So that's just that once per revolution vibration, which may come from the shaft due to unbalance, but maybe the shaft is bent, and there's other possibilities which would just give us this grey vibration from the grey shaft. And again, if there was more vibration, we see a change. And that's what condition monitoring is about, actually. We like to see what the vibration's like to begin with, but we love to see how it's changed, because if I can see a change in one part of the signal, in one part of the vibration, I can say, it's got to do with unbalance and not a bearing problem. Anyway, so there's the vibration that's just from the shaft, and there's the vibration just from the bearing. Now, it's a simplification of what it looks like, but we're just going to say that there's one unique vibration, source of vibration from those bearings. In actual fact, there's a few. If the bearings were in good condition, hey, we wouldn't expect any vibration at that unique frequency. As those balls just roll along, or the rollers roll along, there is no special vibration. But if there is a problem, we get some vibration at a unique frequency. As I said, it's actually 4 unique frequencies for bearings, but we get this green source of vibration from our green bearings. And likewise, as we just went through with the fan, this one has more blades on it, but we can see that, you know, if the fan was all uniform, the blades were all smooth and the airflow was good, we might not see much of this vibration. We probably will see some, but if there was more of a problem, then we get higher amplitude. But as you've seen, when we combine all 3 sources of vibration, which is this red signal here, that is what we get from the vibration sensor. So when we put the accelerometer on the machine and we look at just the raw time waveform, just the raw motion of the machine, this is what we're actually seeing. But of course, what we'd really like to be able to see is the orange vibration, the green vibration, and the grey vibration, because if we weren't seeing any green vibration, we'd say, terrific. But as that starts to develop, we say, oops, we've got a problem here. You know, what does that mean? What should I do about it? How quickly is it changing? All those sorts of condition monitoring questions. And that is what the spectrum is for, because what we're looking at is a change in time along this axis and amplitude in this axis. But I can rotate this around a little bit. What I'm actually doing here is, okay, we're looking at basically the same thing from the side view, but now I'm looking at it from a different perspective. So here's the time again along here. Here are our 3 sources of vibration, but they are separated according to their frequency. Low frequency is the grey one. Higher frequency, in this instance, is the green one from the bearings. And because we have so many blades on this fan, it's an even higher still frequency from the fan. That's that orange vibration. Along this axis, therefore, is the frequency. Low frequency from once per revolution and so on. And what I'm going to do now is look at things from this perspective. I'm going to look at the waveforms end on. It's the easiest way to think about what an FFT does. If we rotate that around, there is the spectrum. And you can imagine that behind that one is that grey sine wave, and behind this one is the green sine wave, and behind here is the orange sine wave. In the FFT process, the simple way to think about it is we're cutting off the bottoms. It's a little more complicated than that, but that's what you're looking at with the spectrum. And you know, we can take it a step further, make it look a bit more like a spectrum. Here's our frequency down the bottom, and there's our vibration. So again, if we didn't have any bearing problems, we wouldn't see that there. and then the peak starts to rise up as the bearing fault develops. A nicely balanced machine, we start with a nice low peak there. We'll generally have a peak, but as the unbalance, let's say, gets worse and worse, as dirt builds up on the fan, we get a higher amplitude peak at the running speed. This is the running speed of this little simulated machine. It is 1 times the speed of the machine. We often call that the 1x peak. And down here, let's say we've got, I forget now, 14 blades on this fan. This will be 14 times, well, in fact, I can look at the scale and I can even work that out for myself. That should be sitting right at 10 times the speed. So we've got 10 blades, 10 times the running speed is 300. I haven't got it quite lined up perfectly, but because I can alter the frequency just a little bit. There you go, that looks better. And so at 10x, 10 times running speed, we've got this peak that's due to the fan. Now this is a very simple view of vibration, but now when you look at a spectrum, you can look at those peaks and say, oh, okay, I know basically where those peaks are coming from. There is a complication because the vibration is rarely pure and smooth. You know, that sine wave was just this perfect, beautiful sine wave. If the machine, let's say, is not uniformly stiff, and or we could go into a bunch of detail, basically the sine wave is no longer nice and smooth, and we end up with something called either harmonics, which is multiple peaks, and you'll see an example of that in just a moment, or we see sidebands if the amplitude of that signal is not constant. It rises, falls, and we'll see little peaks on either side of the big peaks. But that just, you know, we can look at the spectrum and we can see those additional peaks and interpret what they might mean. And ideally, our minds can travel back inside our machines and we can think, ah, I know why that would happen. You know, there's a particular reason. Anyway, let's move along. So here are some real simple, you know, looking spectra. If under normal conditions, I'm just going to say, you know, the bearings are good, everything's good, it's properly balanced, we'll have some sort of a peak at the running speed. And I don't really care what frequency that is, whether it's CPM or Hertz, I don't care. You tell me it's a 1x peak, my mind switches into that mode and I can think, okay, it's to do with the turning of the shaft, could be bent shaft, could be unbalanced, there's a few things. But if I did have unbalanced, then I expect that peak to rise. And predominantly, the main change will be that 1x peak. I might see some little peaks here. Misalignment, we could talk about all these faults in a lot of detail, but I tend to see a change at 1x and twice running speed, and 3 times, and sometimes 4 times, and 5 times, you know, depending on the nature of the misalignment, the nature of the coupling, we'll see the pattern change in a certain way. If there was looseness, the bearing, you know, kind of rattling around, is the simplest way to describe it, I can see lots of peaks, and I can even see the bottom of the spectrum rise up like this. And that's a telltale sign that there is impacting going on. And in fact, these peaks might all be very high in amplitude. I've shown them here sort of dropping down and so on. They might be all very high in amplitude, and they will go on to 10x and 11x and 12x and 13x. Classically, people see harmonics and think, oh, it must be looseness, but it's only looseness if it's the harmonic strong harmonics of 1x, and ideally I'd like to see the noise floor lift up a little bit. For bearing fault, we typically have impacting going on. It's not nice smooth vibration, so in addition to the one peak related to the Adderay's problem, and we'll talk about that more in just a second actually, but there's harmonics. So that's what I'm expecting. And I'm expecting that peak not to be an exact multiple of 1x. So you can see it's 3.1x. It's very common to see a non-integer multiple. And with resonance, I might still see the 1x peak go up, but the resonance is amplifying it. Anyway, we can't explain all fault conditions and so on in a webinar like this, but that's the main thing we're looking at with spectrum analysis. Now, spectrum analysis is great. We can, as long as we measure the vibration properly, we can compare measurements and see what's changed. Which peaks are new, which peaks have changed in amplitude, and what does that pattern look like that gives me an indication of the fault condition. But there are lots of fault conditions that can make the spectrum change in similar ways, and then we have to start, we might compare the vertical vibration to the horizontal and the axial and get an idea where the vibration's coming from. You know, we can make good decisions with the spectrum alone, absolutely, but the machine is telling us much more, and I think it's wise for us to listen to everything the machine is saying. So the spectrum's great, it's a simplification of the vibration, but we can go further. The first thing I want to mention is that we can specifically listen to very high frequency vibration. Now, here I've got, and I hope it's coming through the webinar software and everything okay, but as the shaft turns and the balls roll around, if there was damage right here on the outer race, as each ball comes into contact with that particular point, it generates vibration, but this white wave you see rushing out, we can call that like a stress wave or a shock pulse. It is very high frequency. It occurs when you have metal-to-metal contact. We see it with bearings and we see it with gears, and there are some other fault conditions as well. But when there is only slight damage to the bearing, the simple way to put it is that the vibration in the normal frequency range where people normally measure will not change. You will not see that there is a fault developing in the bearing. Instead, what we want to do is listen to the very high frequency vibration, and I'll mention a bit more about that in a sec. So that's if there was a fault on the outer race. If it's on the inner race, thankfully that's a different frequency, and when the problem gets worse we would see it in the spectrum as I've described, but in the early days we want to pick up that stress wave, which has some differences. If there was a fault on the rolling elements themselves, then we will also see a stress wave, but there are differences in the amplitude and the frequency. And by the way, I'm going to be re-recording this, so generally in the re-recording for sure you see the animations a lot better, and you'll get an email about that. Okay, so basically these high frequency techniques, you may have heard of demodulation or enveloping, shock pulse, peak view, spike energy, HFD, C, SWAN, and there are other techniques. And they all basically work on this principle. What we're going to do is filter out all the low frequency vibration from the unbalance and misalignment and these sorts of faults, and we're just going to focus on what is quite high frequency vibration at a very low amplitude. And those techniques are sensitive and therefore give us a nice early warning of the problem. So that's great. And we can end up with a spectrum from this with just those frequencies, and we can use it. But wait, there's more. The time waveform shows us exactly what's happening inside your machine from moment to moment. This is a sample time waveform that I'll explain. The time waveform can give you a lot of really good information about what's happening in the machine. The biggest challenge with time waveform analysis is making sure that you collect the data correctly. In order to get a spectrum, you must get a time waveform. And it's really just a case of saying to your analyzer, keep that time waveform. But without going into the details here, you have to check your spectrum settings to make sure you're getting good spectra and that you get a time waveform that's worth keeping, because you might be able to see in my little simulation here, there's my damaged gear. Those red dots indicate when the system is actually taking a measurement that goes into the time waveform that then would turn into a spectrum. And you can see that where this big spike is, I'm not getting many red dots, and therefore the digitized thing you're looking at does not give you the information you need. So enough said about that. You just need to make sure that you collect good data. If you have a bearing fault, for example, and as that ball rolls along and there's damage on the rolling element, and we look at that from a time waveform point of view, we can see that the time waveform seems to rise up and fall down, rise up. You can see there's lots of little squiggles. It's very complicated, but the fact is that if I look at that time waveform, I get a very good sense of the severity of the problem by how many G's of vibration I'm seeing, and this rise and fall, this pattern you can see here is telling me a lot about the nature of the problem. If, for example, I've got problems with a gearbox, well, here I can see this change. This rise and fall here is one set of gears turning. The little spikes in between are another set of gears turning. And again, I can look at the spectrum and I might see some side bands. There's an example of side bands that I mentioned earlier. But the time waveform tells me exactly what's going on. I can learn so much more from that time waveform. If I did have looseness, you might be able to see that shaft and the inner race bouncing around. The time waveform's got these big spikes in it, and there's all those harmonics we saw earlier. Sure, I can see all those harmonics and I might conclude looseness, and it would have been correct. But if I could also see that time waveform, I would be left with no doubt what's going on. I would know exactly what's going on. And here's the one we saw earlier. You may be able to see just in this area that these two teeth were damaged. Well, when all of these good healthy teeth go through the mesh, the gearbox thinks everything's fine and the vibration thinks everything's fine, and that's what the vibration is between these spikes. But when the teeth go through the mesh, we get this spike of vibration. Now, if I could look at that time waveform and I can see that once per revolution I'm getting a spike, that tells me that there are some teeth that are damaged. And I can see whether it's one spike or multiple spikes. There's lots of things I can learn, but that tells me exactly what's happening inside the machine. This time waveform is, you might think, oh man, there's little spikes, there's big spikes. You know, based on the amplitudes and based on the fact that it's fairly uniform, that's a time waveform that I would look at and say, don't need to look at it anymore. There's nothing interesting. If I know I'm collecting it properly, it's all cool. This is actually this gear when there are no broken teeth. That's actually a sort of a zoom in on this particular area there. So it's just healthy. I would look at it for 2 seconds, move on. That's fine. Okay, so we've looked at the time waveform and it tells us a lot. But if we stand back for a second and think about the machine as a whole and the structure that's supporting the machine, those forces to do with unbalance, misalignment, resonance, looseness, and other types of faults all generate forces on that machine which are transferred to the structure, which can make it bounce, sway, rock, and move in all sorts of ways. And I can look at an individual spectrum and get an idea of the frequencies, and same with the time waveform. But I would really like to see how the fault condition is affecting the machine as a whole. And that is what phase analysis does. Instead of just seeing some peaks in the spectrum and try to figure out what they mean, for example, if I saw a change in amplitude at 1x, 2x and 3x, I could mount a case that it could be unbalance of different types, misalignment, eccentricity, bent shaft, cock bearing, foundation flexibility, looseness and resonance. It could be any of those fault conditions. And sure, we can do some extra analysis and do some things, but phase really tells us exactly what's going on. Because, for example, if there was static unbalance, we would see, you know, we're sort of looking at the rotor side on. It's the unbalance is making it want to move in a circular motion. Notice that both ends, that both bearings are moving up and down at the same time. Phase tells me that. You can see that as it's moving, it's trying to move in a circular motion, and even though the bearings are stopping it from moving that much, the forces are still there. We can pick those up. So if we could put one sensor here and one sensor down the other end, we would see that both ends of that shaft are moving up and down together. They are in phase. If I compared the vertical motion to the horizontal motion, because it's 360 degrees in a circle, 90 degrees is the difference between vertical and horizontal, I would expect to see a phase reading which is about 90 degrees. Now, we don't have time to go into the detail of how you collect phase, but it's very easy with a two-channel analyzer, a little more difficult if you've only got a single-channel analyzer. But then we can do an examination, and we use these little symbols. The little stick at the top just tells me that from this side to that side, they are in phase. I could write down the actual measurements that I took, but the main thing is this just tells me they are in phase. You can see there's two over here, one up, one at 3 o'clock, 12 o'clock and 3 o'clock. That's 90 degrees, and that would tell me again that it's unbalanced. So this tells me it's unbalanced, this tells me it's statically unbalanced. In this case, I've got dynamic imbalance or unbalance. The bearing on the shaft is still trying to move in a circular motion, it's just that they're out of phase from one end to the other. And we can pick that up as well. So we still see 90 degrees phase, but from one end of the shaft to the other, it's not exactly 180. That would be couple unbalance. If they were in phase, that would be static. Somewhere in between, it's dynamic. Bottom line is you have to balance it. The amplitude in the spectrum would tell you that, and we will use a two-plane balanced job because we know it's dynamic unbalance. Anyway, this is what phase tells you. If you've got an overhung rotor, what tends to happen is that in addition to that circular motion, the rotor wants to rock, as you can see exaggerated here. It wants to rock back and forward. So this time, in addition to vertical and horizontal vibration changing, we see axial vibration changing. And we can, again, do phase readings by comparing the vibration in these axial directions on the bearings and see what's happening. Now, this is a bit complicated, but I can see 90 degrees phase shift at this bearing, 90 degrees phase shift at that bearing. These aren't in phase, but when I compare this axial reading to this axial reading, they are in phase. Now, I might be throwing you in the deep end, but what I want to just show you is that these phase readings are easy to take. If you've got a two-channel analyzer, very easy to take, and they confirm your concerns. A time waveform wouldn't tell you a great deal if it's unbalanced, doesn't tell you anything that you couldn't see in the spectrum for this particular fault condition, but phase gives you absolute confidence that you need to go out and balance that rotor. If we have misalignment, okay, simulated situation here, but you can see that the motor goes up and the pump goes down and vice versa. There is a 180 degree phase difference from this point to this point. If it was angular misalignment, although I don't show the motion here, we create axial forces, which means if I compared the phase from here to here, I would see that they are out of phase. And there's special precautions you've got to take with phase readings, but now's not the time. Eccentricity, okay, the animation is exaggerated, but that also creates a certain phase relationship. We want to know that it requires a correction to the pulley and not unbalance. So if we looked at the phase, we don't get that 90 degree relationship anymore when we compare vertical to horizontal. We get it either in phase or out of phase. Hard to explain in a short time, but that's what we see. With misalignment, we don't see a 90 degrees phase relationship either, mostly just with unbalance. If the bearing wasn't installed properly and was cocked on the shaft, that motion that we can see, again, it's exaggerated, but it creates axial vibration and a certain phase relationship. We'll see that it's out of phase. If we moved around, okay, not a great example because you wouldn't want to be putting a sensor between the belts, but we would see a certain phase relationship. On the other hand, if the outer race was cocked inside the bearing housing, then we would find that if we compared 2 points on opposite sides of the shaft, we would see a 180 degrees phase difference. It's either between here and here, or here and here, or here and here, but we'll see it predominantly in one axis, the axis that this bearing is mounted. Now, I'm going to very briefly mention one other technique for those out there with journal bearings, and particularly with your large steam turbines, gas turbines, compressors, and so on. There is something else we'd like to know, because unfortunately, if we walk up to one of these machines and we put our accelerometer on the bearing housing, we will see vibration, but it doesn't give us a very good indication of what's happening inside, because this is the bearing and this is, well, the journal within the bearing, but let's visualize it as the shaft spinning. We have this little pillow of oil that's set up, this little oil wedge. So any motion that we see due to unbalance or any sort of problem, the motion is deadened because it doesn't transmit through the oil to the housing. It's not as sensitive. So if we just measure from the housing. So instead, we use these probes called proximity probes or non-contact eddy current probes. And what's actually happening is this is measuring the distance, or sensitive to the distance between the tip of the probe and the shaft. We use triangulation, so we use two of them mounted 90 degrees apart. And we use a third sensor because we love to use phase in this application, and this would be mounted somewhere else along the shaft looking at a keyway or something like that. So this is called the key phaser. Bottom line is that using this information we can tell exactly what's going on. This is a very bad situation. We've got oil whirl. The shaft is actually tracing around the bearing. We've sort of established a wedge of oil, but it's moving at the full radius of the bearing. And you know, if we had our prox probes on there, we would see exactly what's going on. And there's lots of other fault conditions. Normally, it should just move, you know, in just a small motion sitting on that oil wedge. We can also consider the entire rotor. You know, you might think, wow, does it really flex that much? Well, hey, like all my animations, I exaggerate, but this might be the first mode. You know, the first balance mode is sometimes called first bending mode, but it's not technically correct. Not the time and place to talk about it. But anyway, you can see that it's moving in a certain way, and if we could, we would like to see how it's moving. And we'd like to see whether it's because of oil whirl or a bit of unbalance or preload or whatever it is. We're interested in what the shaft's doing. And putting two probes gives us that view. That green shape you see is called an orbit. It's comparing the X vibration to the Y vibration. And if we were able to take multiple orbits along this shaft, we would see the shape of the orbit changed. Now, that's just a real quick introduction. It's still using vibration analysis, but for this application, we do it a little differently. Okay, now there's a few key points I'd like to go through. Sorry, these slides are a bit boring. Spectrum analysis is the most commonly used vibration analysis tool. As we've seen, the peaks generally relate to components within the machine, the fans, the pump vane, the blades, the bearings, the gears, and so on. We like to look for changes in the pattern to determine if the condition has changed and how it has changed. We like to look at the amplitude of those peaks to assess the severity of the fault condition. But we should think about other sources of vibration, as in from the time waveform and phase and so on, and we should use other condition monitoring technologies to get the complete picture. Hey, look at the oil if you can, use ultrasound if you can, use thermography if you can. The time waveform shows you what happened from moment to moment. As those balls roll around, as those gears mesh together, all those sorts of things, we get to see exactly what's happening. It really gives you a unique perspective. It can tell you, it can clarify what's going on inside the machine where the spectrum may give you inconclusive information. Too few people utilize time waveforms. They're not used commonly enough. You really should be using them. It doesn't take you any more time to collect it, and it can take you all of 2 seconds to look and see if it's telling you something unique, and if it isn't, you'll be very fortunate. You'll be able to learn something you couldn't learn otherwise. So there's a lot we could talk about the analysis process, but not now. Phase helps us visualize the motion. We can distinguish between different sorts of faults, because otherwise if we can't distinguish them, we might say, hey, go and align that machine. Oh, it's still making that vibration. Go and balance it. The most common reason for balance jobs not succeeding is that the machine was never out of balance in the first place. But we can look at eccentricity and other sorts of faults as well. But it's also important to understand that vibration analysis can be used just as a troubleshooting tool, and in my opinion it's used that way too much. It's just there to sort of find out, oops, we have a problem we have to deal with. We call it predictive maintenance or condition-based maintenance, but it's basically reactive maintenance. We're just finding out that there's a problem that shouldn't exist, and if we don't use the technology properly, we are finding out there's a problem without a lot of time to, well, react to the problem. More time we have, we can plan to pull the machine down at the time that's most convenient to us, or maybe we even last to a shutdown. We can order the parts, we can make sure that the right people are available with the right tools, etc. So what we need to do is detect those faults as early as possible so we can reduce the maintenance cost, improve safety, and increase uptime. But if we can use it to detect the root causes like unbalance and misalignment and lubrication problems and so on, and do something about it, if we can use it for acceptance testing and as a sort of a quality control tool, if you like, when bearings are installed or machines are aligned, check it then, make sure the job's done properly, use it as a supporting tool, and then the machine will run smoothly and we'll detect less bearing faults. So, thank you very much for viewing this presentation. I do apologize for all the issues we've had. I will be re-recording this presentation, and I promise in that case we won't have any problems. And one other thing I'd like to mention, we are just about to launch a new series of, well, sort of emails and presentations called 9 Minutes of Knowledge, because as you've seen, this presentation has taken a lot more than 9 minutes. So what we've done is taken a whole lot of vibration topics and reliability improvement topics, focused in on individual issues, and I promise to take no more than 9 minutes in each presentation. So it's just a really good way to just get the facts, share it with other people. So you'll see that very soon. But thank you very much for viewing this presentation. I do apologize again for the technical issues, and I hope you found it useful. And if you guys have got time, I've got time for questions, but I'm not sure if that's going to work okay.
All right, everyone. Jason, thank you very much. We have reached our allotted time, but we do have some questions that have come in, so we do understand some of you may need to jump off due to time constraints. Again, I want to let you know that this presentation is being recorded. We will send it back for future playback to anyone. You can also go to www.reliabilityweb.com, click on the tutorial section, and you'll find Jason's presentation. Jason also mentioned that he's going to record it and send it out to everyone that is on this list here. So, Jason, are you okay to go into some questions?
Yep, for sure.
Okay, so we're going to go into questions. If you do have any for Jason, you can text them in your upper right-hand corner, and then we'll read them off to him and try to get some answers. Jason, the first one is coming in about softfoot. Could you kind of explain what that is?
Okay. If you imagine a motor, if you could look at the motor sort of side on and imagine all of the feet, ideally all of those feet would be in exactly the same plane. One wouldn't be longer, one wouldn't be shorter, one wouldn't be on an angle. And then imagine if you could look at the base, and hopefully the base that you're mounting it to would be perfectly flat. In reality, that's probably not going to be the case, and that's called soft foot. Soft foot may be because the base is bent or warped, maybe because there's been some welding done or it just hasn't been mounted properly or grouted properly, and it can occur because the feet are bent because of poor castings that might have been damaged. So when you sort of finger tighten the bolts, the hold down bolts, and then fully tighten them, it shouldn't take much of a turn to get the torque correct. If you find that you're turning it quite a bit, that's soft foot, and you are twisting the case of the motor or the pump or whatever it is. You're causing damage, you're affecting the alignment of the machine, but that ultimately is what soft foot is. I've got some great animations, but I just can't grab them in just a second.
Jason, this listener is wanting to know, is vibration analysis one of the condition monitoring techniques?
Yes, absolutely. The condition monitoring basically means we are assessing the condition on a routine basis. So we might take vibration readings every month, and we will compare the condition that we've learned from those vibration readings to previous readings to see how the conditions changed. There's no doubt that we can look at a single vibration reading and learn quite a lot. But every time I look at a vibration reading, I think, gee, I wonder what this used to look like. Are those peaks normal for this machine? I might sense a problem, but is this a problem that's got a lot worse over the last, weeks and months, or is it something that's been developing for a long time? And all of that information tells me about the condition, and it allows me to make informed decisions.
Jason, is there a criteria for the high frequency techniques or peak values?
It is more complicated, unfortunately, because different companies measure that vibration in different ways. When I say measure, we'll all put a vibration sensor on, but the sensor itself can be different, the way it responds to that high frequency vibration. The filter settings we use to remove the low frequency vibration, the way we extract the high frequency information. Peak view does it one way, enveloping does it another way. So there aren't any very simple hard and fast rules. The bottom line is that for most of our machines, we wouldn't normally be generating vibration at those high frequencies. So if you take one of those high frequency readings and the spectrum you get just kind of looks noisy with just some little peaks, cool, everything's good. If the noise floor lifts up, that's a lubrication problem. If peaks start to appear, then we say, okay, something is causing impacts. If they relate to the bearing frequencies, well, it's bearings. If it relates to the running speed, you might have a looseness problem. If it's at the gear mesh frequency, that's because the gears, as they mesh together, we're getting sort of metal-to-metal contact and something's up there. We can see rotor bar problems. So there are different ways to interpret it. We can look at the time waveform and the spectrum from that high frequency information. It's a very powerful tool. One quick comment. It is very important to measure it properly. If you take a sensor with a magnet that's not very strong, put it on a dirty machine that has multiple layers of paint and maybe even some rust and stuff, those high frequency measurements don't work nearly as effectively, and in the early stages of a fault, not at all. The high frequencies don't make it through all those layers of paint and grit and into a magnetically mounted sensor. So do look at that.
Jason, can you go a little bit more into altitude angle?
Into what, sorry?
It says altitude angle.
Altitude angle. I guess the answer is no, because I'm not quite sure what you're referring to. I've been in an aeroplane flying up at an angle, but I don't think that's probably what is being asked. I'm sorry.
Okay, if you could define that a little bit more, listener, then we can ask Jason that. Jason, how do you recognize a problem on the base of an orbit shape?
Okay, well, under normal conditions, the shaft is going to move in a circular motion, and it's going to sit on that oil wedge, and what our prox probes will tell us is that it is moving perhaps in a slight elliptical shape, but if you think about that circle that we saw before, that orbit, it won't be very large. That means that the amplitude's not very high. But if we see a change, for example, if it's still elliptical, just a little bit off sort of circular, just slightly elliptical, but much bigger, we can say perhaps there's unbalance. But that orbit shape can actually squish to become far more elliptical, and it can be tilted, and that might indicate, for example, misalignment or some other sort of preload condition. If it gets very large and we know the clearances of our bearing, we might know that it's oil whirl, for example. We can tell by the shape of the orbit if there's a rub and other sorts of conditions. Because the beauty of the orbit, it's like time waveform analysis in that it's telling us exactly what that shaft's doing. It's just that we use two probes so that we're kind of triangulating that motion and really tracking that whole motion. So you can imagine if there was a rub, that motion isn't going to be as circular anymore. It's not just moving around a circular motion. When it rubs, the orbit or the path changes, and therefore the orbit shape changes. So there aren't the same sort of hard and fast rules. You know, we have our vibration charts, which are only just so good anyway. Orbits, we don't have quite the same sort of hard and fast rules, but there's no doubt that we can see certain changes in the orbit, and we at least know what the shaft's doing, and we can interpret what sort of a fault condition that might mean.
All right, we have time for one more question, Jason, and this is a big question that has come up a lot during this presentation. How often should vibration be checked?
Good question. Okay, now the short answer is that you should think about your machines, think about the fault conditions or the failure modes that you are concerned about. And you need to take measurements frequently enough to ideally get at least two measurements while that machine is transitioning from being healthy to failing. That's the minimum you want to achieve. Now, for a lot of your balance of plant, you know, motors and fans, the faults do develop quite slowly. And so every 30 days would be fine. But it is all about taking measurements frequently enough that you get to see that the change occurs. Now, if you've got a really high-speed machine, things can go wrong very quickly. So you need to take measurements more frequently. So it does take a bit of an understanding of the nature of the failure modes. And that's, you know, a part of our training to just make sure people understand what could go wrong and how quickly it goes wrong. You know, in the case of our steam turbine, things can go bad very quickly. So in that case, we use protection systems. Well, in essence, we're taking measurements constantly. It's called continuous monitoring because things can happen so quickly and the ramifications are so serious, we take measurements that frequently. Other machines, you know, we can measure less frequently. But if we realize that the failure could occur quickly, we might use some sort of online monitoring system. A lot of people think that the measurement frequency has to do with the criticality of the equipment. From a pure vibration analysis point of view, the criticality is not an issue. It's the failure modes. We have to take measurements frequently enough to detect that it is failing and so that we have time to do something about it. Criticality is what you use to justify the expense of the monitoring. So you might say, hey, I would like to monitor this equipment more frequently. Technically, I should, but because of its low criticality, I'm going to take more of a risk and measure it less frequently. I can't afford to measure it as frequently as I would like, and that's just a risk decision. That's just a decision to say I can't justify testing it more frequently. But that's the main thing. It's called the PF interval. You know, P, potential failure, F, functional failure. Between those 2 points, the point where we can detect it and the point where that machine should no longer run, it's no longer performing its function, we need to take at least 2 measurements. We'd like more. The earlier we can detect it puts us in a strong position to take the desired action. The right person doing a good job with the right tools, with the right parts for the minimum cost and the highest level of safety. That's our ultimate aim.
So if we did not get to your question, the good news is Jason Tranter gets all these questions. He's very, very good about replying back to everything. And then I also just want to mention up on your screen, as Jason talked earlier, there is a wealth of knowledge and additional presentations up on MobiusInstitute.com. And then if you want to ask Jason something direct, just go to jason@MobiusInstitute.com right on the screen there. Jason's email is jason@MobiusInstitute.com. or go directly to the website at www.mobiusinstitute.com. Again, this presentation has been recorded. We will send it out to everyone here very shortly, and I apologize for some of the delays that we had today, but thank you everyone for sticking around, and thank you for Jason having another magnificent presentation and a great topic.
Thanks very much. Thank you. Thanks for attending.
Everyone have a good rest of the afternoon, and thank you for logging into another Reliability Roadmap webinar. Have a good day, everyone.